Hello, this is Jack Jackson. In this video, we're going to be talking about implicit differentiation. So this is the last section in this series of videos talking about how we can come up with derivative shortcut formulas. So let's start by considering this example. Let's take the relation x squared plus y squared equals 25. Now, from your pre-calculus studies, you should immediately recognize this as the equation of a circle centered at the origin that has a radius 5. Notice that this is a relation in x and y. It's a set of ordered pairs. There are a set of ordered pairs that make this true. The shape of that actually is a circle. But it's not a function. Y is not a function of x. X is not a function of y. It doesn't pass the vertical or the horizontal line test. We can't solve for y in a single equation in terms of x, nor can we solve for x in a single equation in terms of y. But we can graph it in Graphmatica, and you just pretty much type it in pretty much like it looks, except you use the little Shift 6 caret thing for powers, and you get this graph. So there's our graph. Now here's the question. Well, first of all, we'll come to a question in a second. First of all, notice that this is what we call an implicit relationship between x and y. If we could solve for y in terms of x with a single equation, that would be y would then be an explicit function of x. But here we have an implicit relationship. It's a relation in x and y, an equation with x and y's in it, which certainly has a set of ordered pairs that are solutions to it, but it's not necessarily a function. Now here's the question. Does a tangent line to this relation still make sense? Well, certainly this is a circle, and where we first start with the concept of a tangent line is way back in geometry when we're talking about tangent lines to a circle. So certainly a tangent line makes sense here. And of course, unless it's a vertical line, all those tangent lines have slopes. And so we could talk about the slope of that tangent line, and then of course we could call the slope of that tangent line dy over dx. So dy over dx still makes sense. Now, one of the ways we may look at this function is if we could look at it this way as a graph. If we restrict our attention inside some other circle here, like say just inside this red circle, and we only look at this part of the graph that's right here inside that red circle, then in fact y is a function of x. So we would say that y is locally a function of x. Okay, so how do we use our derivative shortcut formulas to find a derivative dy over dx, and how do we use that to find, say, the slope of a tangent line to the curve, say right in here, for example? Well, the answer is we use the technique of implicit differentiation. Let's see what that means. So we're looking for dy over dx. So we're thinking of x as being the independent variable and y as being the dependent variable, so that y is at least locally a function of x. So notice the variable that's in the denominator is the one with which you're taking, with respect to which you're taking the derivative. Okay, so to perform this, what we're going to do is take our equation, whatever it is here, here's our equation, and we're just going to take the derivative of both sides with respect to whatever that denominator variable is, in this case with the x. Now, anytime you have a y in there, remember y actually changes as x changes. So y is not a constant. Y is at least locally a function of x, but it certainly changes as x changes. So we have to remember to apply the chain rule. So we treat y just like we treated u in our substitution. So it's like you did a substitution, and you do the chain rule. Okay, and so here are the steps to finding the derivative. So what you do is you start by taking the equation like it is, x squared plus y squared equals 25. You don't necessarily have to solve it, try to solve for x or solve for y or get 0 on one side. Just leave it like it is, or any form that's equivalent. Take the derivative of both sides with respect to x. I'll do the easy side first. The derivative of 25 with respect to x is 0, because the derivative of any constant with respect to x is 0. Now here we're going to apply the sum rule on the left. Derivative of the sum is the sum of the derivatives, so we have the derivative of x squared plus the derivative of y squared. Well, the derivative of x squared with respect to x is 2x. the x's match, so we don't have to apply the chain rule here. However, if you did, it wouldn't matter. The next part, if you did the chain rule, would be dx over dx, which of course is just 1. Here, however, we're going to need to apply the chain rule on the next term. The derivative of y squared is 2y times the derivative of the y, and the derivative of y, of course, is dy over dx is what we're looking for. So what we want to do is we want to get this set up here, and then we want to solve for dy over dx. So we add negative 2x to both sides, and then we divide both sides by 2y, and in this case we can simplify slightly by canceling out the 2's, and so dy over dx is negative x over y, or the opposite of x over y. Now, we have a derivative formula, but notice it is also an implicit formula. It's a formula that has both x and y in the formula, not just x or not just y. So to use this to compute a slope on a curve, at a point on the curve, we need to know both the x and the y coordinates of that point. And of course that makes sense because, look back at the picture, pretty much any x that we pick, there's going to be 2 y's, or any y we pick, there's going to be 2 x's that go with it. We can't just specify just the x or just the y. We have to specify both of them, or at least a sign of one of them, so that we can determine which x and y go together for our point. So we need to specify both an x and y, and then we can plug in this point. So for example, let's pick a point, let's say any point AB, and the first thing we need to do is we need to make sure that the point AB is actually a point on the original curve, and of course we'll put in whatever A is for x and whatever B is for y in our original expression, and make sure that we get a true statement. Okay? And if we do, then of course that point's on the original graph. We can plug in the same A and B for x and y respectively in the derivative formula, and we'll have the slope of the tangent line. And of course once you have the slope and a point, we know how to find the derivative, or once we have the slope and which is the value of the derivative, and we have a point, we know how to find the slope of the tangent line and actually the equation of the tangent line. So, for example, 3, 4 is a point that's on this curve. It's actually the one right in the center of this little red circle right there. Okay, and to prove that it's actually on there, we take our original equation, x squared plus y squared equals 25, put 3 in place of x, 5 in place of y, and see that it works out. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. 25, sure enough, equals 25. So that point does make that equation true. Therefore, that point is on our graph. We know the slope then of the tangent line at the point 3, 5 is found by taking the opposite of the x over y and evaluating it when x equals 3, 4, that should say. And we let x be 3 and y be 4, and we see that the slope is negative 3/4. Then to get the equation of the line, remember it's y equals m, the slope, negative 3/4, times parentheses x minus the x value of the point of tangency, close parentheses, plus the y coordinate of the y point, of the point of tangency. And so we get that. Now, how can we check it? Well, one way we can check this is to check it visually. So I'm going to take my graph, which I did in Graphmatica here, and then I'm also going to graph this tangent line. I type it in basically just like this in Graphmatica. And we should see, if we did it right, it should go through the point 3, 4 is where the two curves touch each other, the original curve and the tangent line. And if we just looked in here really close right in this part, we should see that the curve and the tangent line look pretty much the same, pretty close to each other. And so that for sure is our tangent line. Okay, so here's what I'd like you to do here. I've got 5 more examples, and I've given you a formula for a relation, and I'm giving you a point. So what I'd like you to do is use implicit differentiation to get a general formula for dy over dx. Then verify that the point that I give you is actually on the original graph. Next, find the slope of the curve, or the slope of the tangent line, at that particular point. And then finally, find the equation of the tangent line at that point. And then finally now, graph both the original relation and the tangent line together and verify that you got it correctly visually. Okay, so I've given you several examples here, and see if you can work these out. So write these down, try to work all these out, and then come back when you're done and we'll check them. Press pause now. Okay, so our first example, or our next example, we want to find the tangent line to 3xy squared plus 5x squared y plus 6x minus 2y equals 24 at the point 1, 2. So to find the formula for the derivative, we take the original function like this, and then take the derivative with respect to x of both sides. And this is going to be useful to, first of all, for finding the formula for dy over dx in terms of x and y, and then that'll be useful for finding the slope of the tangent line. So first of all, I'm going to do a lot of this in my head here. So I'm going to start with the easy side. The derivative of 24 is 0 on the right. Next, I use the sum rule, and actually I'm going to work it right to left because that's the easiest. So when I take the derivative of negative 2y, that's just negative 2, but then we have dy over dx, since the y and the x were different variables. Chain rule. Derivative of 6x is just 6. The x and the x are the same variable. No chain rule needed. Now the derivative of the 5x squared y, we're going to need to use the product rule. So I'm going to think of 5x squared as the first factor, and y as the second factor. So it's the first factor, 5x squared, times the derivative of the second, which is just dy over dx, plus the second factor, which is y, times the derivative of the first. The derivative of 5x squared is just 10x. Similarly, we want to take the derivative of 3xy squared. We want to think of that as the product rule. First factor is 3x, the second is y squared. So it's first factor, 3x, times the derivative of the second. Derivative of y squared is 2y times the derivative of y. Plus, now we have the second factor, y squared, times the derivative of the first factor. Derivative of 3x is 3. So now that we've practiced doing these derivatives quite a bit, I'm starting to do a little bit more in my head, but I'm saying it out loud what I've got here. So 3 times 2 is 6, and then I've got an x and a y multiplied together, and then my dy over dx. Here I just reordered this more standard order of 3y squared. Here that's just like it is. I'll write this as 10xy for this term, and that's what we get. Now here's the trick. Okay, so I'm even going to say it here. Type it up. Notice that that after taking the derivative of each side with respect to x, we need to get all of the terms with dy over dx just copy and paste that. So we need to get all the ones with terms with dy over dx on one side of the equal sign, and the terms without a derivative on the other side. And of course we do that by adding opposites to both sides. Then we factor out, we use the distributive property to factor out the derivative, and then divide by the coefficient of the derivative of dy over dx. Okay, so let's see how that works. So we were down to the point where we had the derivative was done, so this is right here, but we want to solve for dy over dx. That's what we're looking for. See, we were actually right here on this third line. Well, the fourth line, I guess, is where we were. So now what we want to do, if it's not got a d, we'll put all the dy's, dx's on the left and everything else on the right. So the 3y squared doesn't have a dy over dx. So subtract 3y squared from the left side, it disappears. But of course you have to subtract 3y squared from the right side to keep that balanced. That one's just all right like it is. So is this one. And then we have the plus 10xy. We're going to get rid of it by adding a negative 10xy to both sides, which puts a negative 10xy on the right, gets rid of that term on the left. We're going to add a negative 6 to the left, which is going to get rid of that. It's going to add a negative 6 over here. And then we leave that here. So these are all the dy over dx's are on one side, all the terms with a dy over dx are on one side, and the terms that don't involve a dy over dx are on the right side. Now, since these are all have dy over dx, and it is multiplication here, remember the chain rule is multiplication here, then we're dividing out the dy over dx using the distributive property, and that leaves the rest of it, 6xy plus 5x squared minus 2, all in parentheses times dy over dx, and if we divide both sides by that, all that's in the parentheses, we get dy over dx by itself, and we get the right side as the numerator. What's in the parentheses here is the denominator. Simplify if you can, but now we have a formula for dy over dx. And once again, it's an implicit formula. You must know both an x and a y coordinate that work. So it turns out that 1, 2 is a point that's actually on this graph. Let's make sure that's true. Take the original function, 3xy, original relation, I should say, 3xy squared plus 5x squared y plus 6x minus 2y equals 24. Put in x equals 1 here, 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 and y equals 2 here, here, and here. Usually it's best if you just put a parentheses around that, put the number in there, do that. Now we multiply this out, or work this out here, and see what we get. 2 squared is 4, times 1 is 4, times 3 is 12. 1 squared is 1, times 5 is 5, times 2 is 10. 6 times 1 is 6, negative 2 times 2 is negative 4. 12 plus 10 is 22, plus 6 is 28, minus 4 is 24. Right side is 24, 24 is certainly equals 24. So that checks, that point is actually on the graph, and we'll see that in a minute. Now to find the slope at that point, 1, 2, we take the slope, the formula that we had for the derivative right here, and we take that formula right there, and we plug in x equals 1 and y equals 2, which is exactly what I have here. Notice everywhere there's a y, there's a 2, and everywhere I had an x originally, now there's a 1. Simplify this out. 2 squared is 4, times negative 3 is negative 12. Negative 10 times 1 times 2 is negative 20. Then we got a minus 6. 6 times 1 times 2 is 12. 5 times 1 squared is 5, and then we got minus 2. 12 minus 2 is 10, plus 5 more is 15. And the top I get negative 20, negative 12 is negative 32, plus negative 6, that's negative 38. I wrote the 38 on front, on the top, put the negative 1 out front. So that is your slope. Okay? And so the equation of the line then is y equals the slope, and negative 38/15, times parentheses x minus the x coordinate, which is 1, plus the y coordinate, which is 2. That's the point slope form of that particular line. And since this is a tangent line, the point slope form centered at the point of tangency is a very good way to write that function. It's at least as good, maybe even makes more sense than, say, the slope y-intercept form or the slope x-intercept form. Although there are, of course, other ways you could write that. Now we graph this and see what we get. When I typed it in Graphmatica, you can see what the graph looks like there, and you can see the tangent line, and the tangent line is at the point 1, 2, and it does look like the slope is correct because it's going along with the curve there. Okay, so if you didn't do the last one, at least try to do the next one now on your own. Find the tangent line to the equation, or to the curve, y times e to the x plus cosine of pi y equals sine of pi x, and do the tangent line at 0, 1. So what you want to do is find the formula for dy over dx, make sure that 0, 1 is really on this graph, find the slope at 0, 1, then use that to find the equation of the tangent line at 0, 1, and then graph both that tangent line and the original one using a graphing utility. Now, unfortunately, your calculators are not really good at doing implicit graphing like this, but there are other programs that are good. One I like to use a lot is the shareware program called Graphmatica. So anyway, you try this one. Press pause now. Okay, so first we're gonna just leave it written just like it is, and we're gonna take the derivative with respect to x of both sides. Let me start on the right side. Derivative sine of u is cosine of u being pi x, times derivative of u. Derivative of pi x is pi. Here we're going to use the product rule, well the sum rule first, then the product rule. So the derivative of y times e to the x is first times derivative of the second, so it's y times the derivative of e to the x. Derivative of e to the x is e to the x, plus the second, which is e to the x, times derivative of the first. Derivative of y is dy over dx. Now we have to find the derivative of cosine of pi y and add that on. So cosine of, say, w, the derivative of cosine w is the opposite, so that plus becomes a minus, sine of the w, pi y, times the derivative of the w. Derivative of pi y is pi times the derivative of the y. Okay, now what can we do with it? Well, we want to get the ones that have the dy over dx on one side and get rid of the other ones. These two with dy over dx are already on this side. We just need to add a negative y e to the x to both sides to cancel this out on the left. And of course that introduces this term on the right side. Then I want to factor out the dy over dx here, leaving me e to the x minus pi times sine of pi y. And then finally divide by this coefficient to get dy over dx is pi times cosine of pi x minus y times e to the x over e to the x minus pi times sine of pi y. Now let's go back to the original function, original relation. Y e to the x plus cosine of pi y equals sine of pi x, which is what I've got written down right here. Now let's make sure that 0, 1 really is on the graph. Okay, so we put a 0 in for x here, and a 1 for y here and here. E to the 0 is 1 times 1 is 1. 1 times pi, or pi times 1 is pi. Cosine of pi is negative 1. Think about a rotational angle of pi. Puts you in the unit circle picture. Puts you on the negative part of the x-axis. It crosses the unit circle at negative 1, 0, and the cosine is the x-coordinate there, so that's negative 1. You can also think about the wave graph and know that it starts at 0, when x is 0, starts up at the maximum, up at 0, 1, comes down to 0 at pi over 2, and it's down to negative 1 at pi. So once you get to pi, that's negative 1 there. So it's 1 minus 1, which is 0. 0 times, or pi times 0 is 0, sine of 0 is 0, so the right side is also 0, it does check. Now to find the slope of the tangent line, which was what we're going to need first to find the derivative, we're going to need the derivative to find the slope, which is going to be required to find the equation of the tangent line. So what we know is that the slope is dy over dx evaluated at xy equals 0, 1. So take this formula here and plug in 0 for all the x's. That happens here, here, and here. And plug in 1 for all the y's, and that only happens a couple times right here, and then down here. Alright, now let's simplify a little bit if we can. Let's see. Pi times 0 is 0, cosine of 0 is 1, 1 times pi is pi. E to the 0 is 1 times this negative 1 is negative 1. In the denominator, e to the 0 is 1. Pi times 1 is pi, sine of pi is 0, 0 times minus pi is 0, so we're adding a 0 there. So you end up with pi minus 1 over 1, which is just pi minus 1. So pi minus 1 becomes our slope. So the equation is y equals pi minus 1 times parentheses x minus the x-coordinate, which is 0, plus the y-coordinate is 1. Since this is 0, I can simplify this to just y equals pi minus 1 parentheses times x plus 1. Now if I graph that along with the original graph, this is a portion of it here, and so you get this kind of funky little shape in here, and some kind of a little weird looking wavy thing down here. But notice that the point 0, 1 in fact is on the graph of both the original curve and the tangent line. Furthermore, that tangent line actually touches, not only is it touched there, it's following the curve right there. So if I zoomed in really close here, these things would look very much the same, which is of course what you want to have happen. Okay? Alright, I think I'm going to stop there and then come back in the next video and finish up the other examples.